The next topic is to look at the motion of a point charge in a constant uniform electric field. The key idea here is that the electric force is usually the only force that's acting, especially in problems, because we usually ignore the force of gravity in problems because the electric force is much, much stronger than the force of gravity. And with the electric force as the only force, motion is really just like projectile motion. So in projectile motion, where a projectile is influenced by the gravitational field to feel the force of gravity, and that force of gravity causes the acceleration to be vertically down. One big difference between projectile motion from mechanics and caused by gravity and the point charge moving in a constant uniform electric field is that the electric field and the electric force can point in any direction versus the force of gravity, which acts vertically down. So for example, we could create a situation where we have an electric field going off to the right. It would be going from the positive charges on the left to the negative charges on the right. And this is one way to actually create a constant uniform electric field, and we'll talk about that a lot more in the chapter on capacitors. If I have a positive charge at the bottom and it has an initial velocity that's upwards, then the electric field is to the right. It's a positive charge, so from F is equal to QE as a vector equation, we'll realize that the force is actually in the same direction. So the force Fe is also going to be to the right. And if the force is to the right, that means that the acceleration will also be to the right. And so if this charged particle is accelerating to the right, acceleration is really just a change in velocity over time. So when the velocity starts out as being vertically upwards, it's actually going to curl parabolically to the right because of the electric field, which creates the electric force that causes the acceleration. The second big difference between projectile motion and the motion of a charged particle moving through an electric field is that the force direction, or the direction of the electric force, depends also on the charge. If you have a positive charge going through a uniform constant electric field, then the force is in the same direction as the electric field. But if you put a negative charge in there, then the force is actually going to be in the opposite direction to E. So I have the same setup as before, and the electric field lines, remember, go from positive to negative. So the electric field is actually to the right. The difference is that now I'm going to have a negative charge, and the negative charge is going to start out at the top and have an initial velocity going downwards. The electric field is to the right. We know the electric force is equal to Q times E. So the electric force is actually going to be to the left. And since the force is to the left, therefore the acceleration is also going to be to the left, thanks to good old Newton's second law. And then that will cause the velocity to change towards the left, and the particle will follow a parabolic trajectory as it's accelerating towards the left side. So when you're solving a problem with the electric charge moving through a constant uniform electric field, there's a certain strategy to follow. And the first thing to do is to separate the x and y axes, because the component of velocity perpendicular to the electric force doesn't change. In projectile motion, this was basically the same as saying the horizontal component of velocity didn't change, and that's because the gravitational force was vertical. The next step is to identify the direction of the electric field. Once you know the direction of the electric field, after that, you can actually identify the direction of the electric force. And so that will be in the same direction as E if you have a positive charge, and it will be in the opposite direction if you have a negative charge. The last step is to identify the direction of acceleration using Newton's second law. And in problems, most of the time, the electric force is the only one acting. But of course, they can always mix things up a bit and force you to include the gravitational force, in which case you have to calculate the net force. And this strategy reflects the causality in the sense that the electric field causes the electric force, that force causes acceleration, and the acceleration is what ends up revealing itself as that parabolic trajectory. Now, it's also possible to work backwards depending on the given information. Sometimes I would, for instance, set up a problem where you don't know which side is positive or negative, and you might, in fact, the problem I can think of right now is in a YouTube video where you don't know which side is positive or negative, but you have a charge that's moving a certain way, and in this case it has to move and hit a fly that's marked at the X up here. And so given that, if we have a positive charge, and I believe in that case actually it's an electron, so I should really represent it that way. If I have an electron at the bottom, and I need the electron to move up and to the right, then in order for the electron to move up and to the right, I would work backwards. I would say, well, okay, the acceleration is definitely to the right, which means that the net force, which in this case it's the electric force, is also to the right. It's an electron, so the electric force is opposite direction to the electric field, which means that in this case, the electric field is actually to the left. Knowing that the electric field is to the left, then I put negative charges on the left side, and I put positive charges on the right side. And it's just a simple, basically a simple thought experiment. It's good for you to be able to work through both ways and to understand the causality, and it just comes with a bit of practice.